All right, let's get into more detail regarding the fats. All right. So fats, or lipids, are compounds that contain carbon, hydrogen, and oxygen. Okay. But they have a different proportion of these elements. So just put in brackets here, but have different proportions. So unlike carbohydrates, for example, lipids are actually insoluble in water because, again, they are in different proportions as well as they are structurally very different due to polarity. And that's what we're going to be going in depth with in this video. So lipids are insoluble. So they do not like water. They are hydrophobic. So they're only soluble in particular substances that are non-polar. So it's only soluble in fat-soluble compounds. For example, acetone. This is also known as nail polish remover. I want you to please look at the video link in the description here, where we go in depth about polarity. So if something is polar or if something is non-polar, and prove how. Because what's interesting is acetone is fat soluble. Insoluble fats can dissolve with acetone because, again, lipids are non-polar. Non-polars only dissolve with non-polars. It doesn't like water. Water is very polar, for example. Acetone is fat soluble. So does this always land true? If something is non-polar, doesn't like water, it's fat soluble, also doesn't like water. You would probably think that would make sense, right? However, there are a few exceptions and there is nuance to this. So just keep watching this video. Alcohol is another fat soluble compound. And ether is another. And chloroform is another. We are going to be looking at all four of these and break them down using Lewis structural diagrams to prove whether they are actually polar or whether they are actually non-polar. You would think just by nature that these all would be non-polar because fats, lipids, are non-polar. So we'll touch base back on these shortly. But you do have to know that you may have noticed how fat floats on the surface of water when you're like doing the dishes, for example, because they are hydrophobic, right? So I'll just put here hydrophobic. So the most common type of lipid, the fat, is composed of two structural units, one glycerol and three fatty acids. Right? This is known as a triglyceride. And this should be a familiar term of vocabulary that you looked at in the previous video regarding micronutrients and macronutrients, right? How they were formed via a dehydration reaction. All right, before we look at polarity using those Lewis structural diagrams, let's quickly look over the two types of fats, saturated fat and an unsaturated fat. So as you can see here, a saturated fat are examples of like animal fats or animal product fats, like butter, for example. In a saturated fat, you see how all of the carbons here are single bonded with hydrogens. So this hydrogenation means that there are no kinks within the backbone. So if you have double bonds, it creates kinks in the backbone. I'll show you why in the unsaturated fat example. But just know that this is a very, very stable line with all of these hydrogens being symmetrical, right? This is symmetrical with this is symmetrical with this, etc., all the way down, okay? The more hydrogen bonds that you have makes it more difficult for it to break down. So this is why saturated fat is very difficult to break down. It's very energy taxing, hence why it's not a healthy fat. Whereas with a double bond, which we'll see later on, you don't have as much hydrogen bonds. The more hydrogen bonds you have, the more solid-like they are. This is why butter is a solid. Margarine, for example, is a plant fat. However, it's hydrogenated by adding more hydrogen bonds to it so that it becomes more solid-like, which is why it's also unhealthy. Because naturally, you're not supposed to be putting extra hydrogen bonds for no reason. But anyway, so let's count them up. So you have your carbons here. Let's start with carbons. So how many are in this backbone over here? We got 2, 4, 6, 8, 10, right? So I'm going to be putting C10. How many hydrogens do you have? Well, I got how many? 2 here. So 2, 4, 6, 8, 9. Okay, so 9 times 2 over here will be 18, 19, 20. So we got C10H20. And how many oxygens do you have? Well, you have one that's double bonded, one that's single bonded. You still have 2 of them though, so it'll be C10H20O2. Now let's look at a unsaturated fat. You notice how immediately you see this backbone is no longer going linear. It was, but then as soon as that double bond appeared, it kind of angled downwards. It got pushed downwards in that direction. Why? Well, you see how there is a double bond. With that double bond, you notice how there are no more hydrogens on either side. Why? Hopefully you've seen in the previous video already, link is in the description. You need to have watched that first. Learn how carbon can only have 4 bonds. So you notice how there's 1, 2, 3, 4 already. Okay, so it can't have another one over there. Okay, same thing with this. Same thing with this carbon, right? 4 bonds. 1, 2, 3, 4. So there's no need to put any other hydrogens. It won't fit. Can't do that in organic chemistry. You can't do that with a structurally sound element like carbon. It's very stable with 4. And you can see here with an example, olive oil, a plant fat, is an example of an unsaturated fat. Very healthy. Heart healthy too. So let's write this out. How many carbons do you see? Well, we got 2, 4, 6, 8, 10. Okay, so we got 10. So we got C10. We got 2, 4, 6, 8, 9, 10, 12, 14, 16, and 18. Okay, so we got 18 hydrogens. Notice how it's smaller now, right? We have less hydrogens on this one. And then we still have 2 oxygens. All right, so this here is our unsaturated fat. Our saturated was H20. All right, so this was sat, this was unsat. Because saturated fats have more hydrogen bonds, it's more hydrogenated, it's less healthy, more difficult to break down. I also want you to know why trans fats are considered unhealthy as well. So a trans fat has double bonds though. However, you see this H, okay? It's not up there. It's now down here. So you see how this can be a problem. Because even though there is a double bond in a trans fat, we're looking at trans fat right now, it is becoming more stable, right? Because if you had 2 H's up here, it's more unstable, it's easier to break down because they're not as balanced. If you change it to a trans fat molecule, you see how the H up there and the H down here cancel out. So it becomes more stable. It balances it out more evenly, so it's harder to break apart. Hence why it's considered very unhealthy. All right, let's look at a couple of examples from those fat solubles, those four fat soluble molecules, and let's determine their polarity to see if they dissolve in fats or not. So let's first look at this one, CH3, CH2, OH. This was the particular alcohol. Is it fat soluble? Let's look at its polarity now. So we have how many carbons? We got 1 there, 1 there, all right. So we got 2 carbons, its valence is a 4 on the periodic table. How about hydrogens? We have 1, 2, 3, 4, 5, 6, all right. And how many valence? Has 1 valence. And the last one is its oxygen. We only got 1 oxygen, okay, and its valence is 6. So we add them all up, you end up getting 20. And then you are now going to subtract that, right? You're going to get that 20, you're going to subtract it by the lowest common multiple of 8 without exceeding that number that you just found, right? So 8 times 1, 8, 8 times 2, 16, 8 times 3, 24. It goes above 20, okay? So we got to use the one below, so we're going to be doing 16. So you add them all up, you get 4 electrons. Sorry, you subtract them, you get 4 electrons. That means your central atom has 4 electrons surrounding it. So you could draw it out this way. You get your 2 carbons. They're the most electronegative element in this formula, not including H's, right? H's are not going to be in the center. They're the only exception. All right, so we got these in the middle there. That means the higher electronegative elements are going to be on the outside, right? Like oxygen, for example. All right, we know that oxygen needs to have 6 valence electrons. So we have one bond over there. We know that oxygen likes to have a double bond. So we'll put a second bond over there as well. How are we going to be filling up the rest? Well, we have to start filling the rest with hydrogens because we got to make those fit. So we've been able to fit those 2 carbons and that oxygen. So let's put in the hydrogens. So we can put in maybe a hydrogen here, maybe a hydrogen there, hydrogen there. So now that carbon has 4 bonds, so it's now happy. And we fill in those remaining with H's. Do the same thing here. So we got 1 bond there, okay? 2 bonds, 3 bonds. We got to have another bond. So we'll put in maybe another one up there. So we've established that it's double bonded, but how many bonds can we have? We can only have 4 bonds. But how many hydrogens can we have? We can only have 6, right? So we already have 1, 2, 3, 4. We got to add 2 more. So we can add those other 2 hydrogens on this oxygen over here because everyone else is already filled up. This one is already quite happy if you were to look at it. Has 1 electron, 2 electron, 3, 4, 5, 6, 7, 8 belonging to that carbon. So it's happy, it's done. This one too. 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is very happy as well. So if we were to add those extra 2 hydrogens, we can put them like maybe there. It doesn't matter. But if we were to count them up, is it happy? Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So are we done? Is this correct? We'll have to preface it that we need 4 electrons on that central atom. Well, where is the central one? Well, out of all of these, this is in the middle, right? This could also be here as well. It doesn't matter. Regardless, this is the most least electronegative atom. That is not a hydrogen. But there are no lone electrons. We need 4 lone electrons. There are no lone electrons here. They're all in bonds. So this image is not correct. So how do we ensure that we have our central element having 4 electrons? What if we put in the oxygen there? So we're breaking the rule. Would it work? Let's give it a try. All right, so we're putting our oxygen in the middle here. We're breaking the rule about the electronegativity, right? The lowest one, not a hydrogen, right? The lowest electronegative has to be in the middle, okay? A very strong electronegative element is now in the middle, but let's give it a shot, okay? All right, so oxygen has a valence of 6, so I'll just put 1, 2, 3, 4, 5, 6. How is it going to bond? Bonds are going to go outwards this way, all right? Now, how do I know that the 2 electrons, that the 2 lone pairs are up here instead of putting this lone pair down here? See the video link in the description about Vesper shapes. We're not going to go into depth about that in this video. Just know that they are on one side. All right, we got to fit in our hydrogens, right? So we got a hydrogen, carbon. Okay, we got a carbon there, we got a carbon there. So is this oxygen happy right now? 1, 2, 3, 4, 5, 6, 7, 8 electrons, okay? So the ones that belong to oxygen right now are very happy. So oxygen's done. So let's do our carbons now. Okay, so it's got 1 bond here for carbon. We got to put 3 more bonds. Same thing here, 3 more bonds. And we're going to fill the rest of them with hydrogens. All right. Does the math check out? Yeah, we got 3 hydrogens. We got 3 hydrogens. We got 6 hydrogens. We're good. And our central one has the 4 electrons. So this is absolutely the correct way to draw it. So let's do our checklist. Is it non-polar? No lone pairs. That's obviously false. There are lone pairs. We have two, right? We got a lone pair there and a lone pair there that are not bonded. So this is not true. So as you can see, one of our checklists is X'd out. So it's not actually very non-polar, right? If both of these checklists are going to be given a check mark, it means it's very, very non-polar. Okay, but one of them is X'd. So it's not going to be very non-polar. Let's look at our second checklist. No hydrogens. Well, that's false, okay? But remember, unless canceled. Unless. All right, unless canceled. Are they canceled? Yeah. This one and this one cancel out. This one and this one cancel out. And technically this one and this one also cancels out, because if you were to extrapolate it, right, that goes that direction, this goes in that direction. It's a net vector. They cancel out. So they do cancel. So unless canceled, yes. Okay? So it's kind of half, right? Is it non-polar? If this was a check, and if this was both, if that was a check as well, it would be non-polar for sure. But because one of them is X'd out, it's not exactly 100% non-polar. It has a little bit of polarity. So this is why this type of alcohol is actually polar, but it can act as non-polar as well. So there's a continuum, there's nuance when it comes to these things. All right, let's look at CHCl3. This is also known as chloroform. So we've claimed at the beginning of this video that this is also fat soluble. Let's see if it's actually non-polar to prove that it's very fat soluble. Well, we got one carbon, so 1 multiplied by 4. Add that with 1 hydrogen, has a valence of 1, so multiply by 1. And we got 3 chlorines, and it has a valence of 7. Add them all up, what do you get? You end up getting 26. All right, so let's do that common multiple of 8 rule. So 26 minus 8 times 3 will give you 24, right? You can't do 8 times 4. That will give you 32. That goes above 26. So it would be 26 minus 24, which will give you 2 electrons. So we got to have 2 lone electrons floating around on the central atom. All right, so we don't have much to deal with, so this one should be pretty simple. Are we going to be using carbon, or are we going to use chlorine as the least electronegative element in the center? Obviously, carbon has a lower electronegativity, so we'll be putting it over there. So the H's are going to be floating around somewhere. So the H's are going to be floating around somewhere, and same thing with the Cl's, okay? And we can actually kind of spread them out this way and see if we have to adjust that. And we already know that carbon has 4 bonds, all right? Because it has 4 valence electrons right over there, okay? So let's bond them appropriately. All right, so hydrogen only has 1 valence, so that's that electron there, so we're good. Carbons are good. Let's look at the chlorines, all right? Chlorine has a valence of what? Has a valence of 7. Okay, so we got 1 electron there, obviously on its own. 2, 3, 4, 5, 6, 7. Okay, same thing with this chlorine. 1 electron there. 2, 3, 4, 5, 6, 7. That we gotta draw these extra ones in, right? Same thing with this one. It already has 1 electron there bonded. 2, 3, 4, 5, 6, 7. Okay, so if you add them all up in terms of their H's, in terms of their total number of electrons that they're owning, everyone's happy, right? 1, 2, for this chlorine, right? 1, 2, 3, 4, 5, 6, 7, 8. It's happy. Same thing with this one. Same thing with this one. It's exactly the same as that chlorine. This hydrogen can only have 2 electrons that it's owning. So it has 1 already on its own, and it's sharing that one too. All right. And then, well, we already said carbon already has 8, right? 1, 2, 4, 6, 8 that it owns. So we're actually done. There's no better way to draw this. So this 2 electrons rule on that central atom, it can't exist, unfortunately. Because every single lone electron that the carbon had is busy bonding, and we can't draw this out in another way. So sometimes this rule has an exception. We don't have to use this. This is the best way to draw it right now. All right, so is it nonpolar? Let's do our little checklist. Well, let's do our first one. No lone pairs. Is that true? Is there no lone pairs? That's true. There are no lone pairs on that central atom. How about no hydrogens? That's false. There is a hydrogen, unless canceled. How about that question? The second part. Unless canceled. Are they canceled? This is definitely not canceled with that one. Obviously, this cancels with that, because if you look at their electronegativity differences between Cl and C here, and this Cl and C here, obviously this is very electronegative, so force would be in that direction. Same thing with this Cl, more electronegative, so it'll be going off in that direction, but the magnitude is the same, because it's the same element. This is a Cl, this is a Cl, and they're both dealing with a common denominator of carbon, okay? So they're going away from each other with the same magnitude. So for sure there's a canceling there. However, this one, however, again, Cl is more electronegative than the carbon, so it's going to go in this direction. But how about the hydrogen? Well, this hydrogen is less electronegative compared to the carbon, okay? So the force is going to go towards the carbon, but it's going to be a smaller one, smaller arrow. Obviously, they do not cancel out. Not only are their magnitudes different, they're also going in the same direction. So obviously that's not canceling. So definitely no canceling is happening. So it's not actually 100% non-polar. It can be treated as non-polar, that's why it's fat soluble, but it still has a polar-like quality. So please just remember that there is nuance. There is nuance to polarity. It's not always clear-cut when we look at solubility for some of the fat-soluble substances.